Pre-Calculus 2.2 Day 1. And so we are going to look at transformations of some graphs, and we're going to look at the leading coefficient test to determine end behavior of graphs and use the real zeros of a function to help us sketch them. And so this first feature that the graph of a polynomial function is that it is continuous. It just means that as you trace it, as you go from left to right, you never have to pick up your pencil and skip over anything and start in a new spot because it has no breaks, no holes, or gaps. And on these first couple of problems, we're going to apply this when n is even, and so n is that exponent of x. The graph is similar to the graph of x squared in terms of end behavior anyway. And when n is odd, then the graph is similar to the graph of y equals x cubed. And so in this first case, we have that exponent is odd. So we're thinking it's going to be closer in nature to that of x cubed. And overall, the x cubed graph, just a quick idea of a sketch, looks like this versus the x squared graph looks basically something like that, just an idea of what it looks like. And the difference is on the x squared, you have both ends are going up. Both ends are going to positive infinity. If it's flipped, then both ends will go to negative infinity. But on x cubed, you've got one of each. One end is going to negative infinity, the other is going to positive infinity. And so that's what we mean. So when we look at a and we have that exponent is 5, I'm expecting like an x cubed graph, one ends up going up and one ends going down. With a negative out in front, I'm thinking, okay, this is flipped. So I'm kind of thinking that it should end up looking more like this, like an x cubed graph, but flipped. And so to go ahead and evaluate this, we can just take a few points, do a t-chart. And I kind of like to think about -2, -1, 0, 1, 2. And if I need to go out further, I will, if it will fit. But we'll start with that and adjust as needed. And if I put a -2 in to the fifth, a -2 to the fifth is a -32, but then I want the opposite of it, so that's actually at a +32. And then at -1, I put a -1 to the fifth, I get -1 times -1 is a +1. And at 0, I have 0, and at 1, I have a -1. And at 2, I get 2 to the fifth is 32, and then the opposite is a -32. Now, my graph doesn't go up to 32. It's just going up to 10. And so I'm just going to go ahead. I could scale it down and go by 2s if I wanted to on the y-axis, but I'm still not going to quite hit 32. I could go by 3s. So 3, 6, 9, 12, 15, 18, 21, 24, 27, and up here I'm at 30. So then 32 is just going to be slightly above that. And so, but I'm just going to go ahead and let the x-axis go by 1s. So this is going to be down at -30. And so if I go to the left 2, I would be up at 32. So that's just slightly off the graph. -1, I'm at 1, but I have to remember I have that vertical stretch. So it's going to be right there. And then 0, 0. And then at 1, I'm at -1, but I've got that vertical stretch, or that scale. So -1's just there. And at 2, I'm at -32. And so I expect it to have that kind of twist that the x cubed graph has. So I want to keep that in mind as I go to graph this. And we call that a change in concavity. Changes from being scooped up to scooped down at 0, 0. There's a change in concavity there. And so there's that graph. All right, and then the next one, since the power is to the fourth, I'm thinking of it as more like an x squared in terms of either both ends are up or both ends are down. And out in front, we have a positive value. So I'm going to just go ahead and make a t-chart. If I know something about transformations of graphs, that x plus 1 to me says, okay, I'm going to be shifting to the left 1. So that might be kind of my center point, and then go -2, -3, and then at 0 and at 1. And I can go further in either direction as needed. And if I put a -3 into there, I get a -2, and -2 to the fourth is going to be up at 16. At -2, if I put a -2, I get a -1, and -1 to the fourth is +1. If I put in -1, I get 0, 0 to the fourth is 0. If I put in 0, I get 1 to the fourth, which is 1. If I put in 1, I get 2 to the fourth, which is 16. And so if I go to graph that, again, this graph only goes up to 10. So maybe I want to go by 2. So this is at 20, and this is at -20. But then I'll let the graph, the x-axis, just go by 1s. So it'll fit. So at -3, I'm up at 16. So if I count down 18, 16 is going to be there. At -2, I am up at 1. At -1, I'm at 0. At 0, I'm at 1. And at 1, I am at 16. And so it should be round, oops, kind of rounded as you go. Thinking of it as a parabola kind of shape, not a V, not an absolute value. And don't forget the arrows on the ends. We take off points for that, for not having that on tests. Oh no. So there's that. And so being able to graph those and kind of have an expectation. But it goes a little further than just n is even and n is odd. We can actually, if we look at the leading term, determine some more about the shape of a graph. And that's this key concept right here. And so in addition to looking at if the degree is odd, if the leading coefficient is positive, I know overall it starts from below, and then it might have several turns, but overall it ends up increasing. And so what we are going to say is, I'm going to reverse this. As x goes to -infinity, then y goes to -infinity. We know that will happen. And that's end behavior. So we know that as you go to the left, the graph's going to go down, versus as you go to the right, as x goes to infinity, then y goes to positive infinity as well. And so just by knowing that the degree is odd and the leading coefficient is positive, I know that happens. And we have this down below. So looking at these, where is the degree odd? And where is the leading coefficient positive? And notice they're all nicely done in descending powers for you. They're already in that order, so that helps. And right here, our leading coefficient is 4, which is positive, and the degree is odd. That tells me that whatever happens, it's coming from -infinity, and it might have some twists and turns, but it's going to end going to positive infinity. I know that the end behavior is going to look like this. So it says describe the right hand and left hand behavior. So what I want for this is as x goes to -infinity, then what happens to y? And we'll write f of x goes to what? And then as x goes to positive infinity, then f of x goes to what? So you need both as x goes to negative infinity and as x goes to positive infinity, but as x is going negative more and more, then y just goes downward to negative infinity. And as x goes to positive infinity, then f of x goes to positive infinity. And that's what I'm looking for when I ask it that way. But then there's 4 cases, because you have when the degree is odd and the leading coefficient is negative, you end up flipping that graph. And so you have just the opposite. We have as x goes to negative infinity, then y is going to go to positive infinity. Versus as x goes to positive infinity, y is going to go to negative infinity because it's flipped. On the other hand, when the degree is even and the leading coefficient is positive, both ends are up. So as x goes to negative infinity, y goes to positive infinity. As x goes to positive infinity, then y is going to go to positive infinity as well. So the y values both go up. However, if the degree is even and the leading coefficient is negative, then we have as x goes to negative infinity, the y value is going to negative infinity. As x goes to positive infinity, the y value, it's going down, is going to negative infinity. So both y values, regardless of x going to positive or negative infinity, the y values are going to negative infinity, or our function, or f of x. So those are the 4 possibilities, just by examining the leading term. So in part A, we have it's negative, and it's of odd degree. So the leading term's -7, and this is of degree 3, which is odd. And so that means you've taken a normal x cubed graph and flipped it, so it is this case right here. So as x goes to negative infinity, then f of x goes to, need to fill that out, and as x goes to positive infinity, then f of x goes to, what does it go to? So you have to think, okay, it's flipped, so as I go to left, the y values go up, 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 so that's positive infinity. As we go to the right, as x goes to a very large number, the graph is going down, 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 so the y values are going to negative infinity. And then in part B, the leading term coefficient's positive, it's a +1, and it's even. And when it's an even degree, the degree of this is 4, and the coefficient's positive, both ends are up. So as x goes to negative infinity, then both ends are up. The y values are going to positive infinity. As x goes to positive infinity, then the y values are going still to positive infinity because both ends are up. And then the one that we didn't do is an example like this, but I could make one up because all I need is a negative leading coefficient, and I need the degree to be even. And it doesn't matter what the rest of it is. And I would know that whatever's happening there, both ends are down. And so whether x is going to positive infinity or negative infinity, the y values are going to negative infinity. All right, so you will be asked to describe the right hand and left hand behavior of the graph, and you should analyze it just the way we did and know that chart, know what the outcomes of that. So now we're going to move on to finding the zeros of a function. And it's one of the most important problems in algebra. And so the real zeros of a polynomial function is when f is a polynomial function and a is a real number, the following statements are all saying the same thing. X equaling a is a 0. X equaling a is a solution when f of x is 0. X minus a is a factor of the polynomial, and the comma a0 is an x-intercept of the graph. So it can be shown that for a polynomial function of degree n, so let's just say we have f of x is equal to 3x to the fifth minus 2x plus 1. So this is of degree 5, just to put it in context. The function f has at most n real zeros. So this has at most 5 real zeros. It can't have any more than that. And then the graph has at most n minus 1 turning points. And if I have this is a turning point. It's a point where the function changes from increasing to decreasing or decreasing to increasing. Right in that vicinity, that's the highest point. It's not the highest point, but it's in that vicinity. Then here's another turning point. Function's changing from decreasing to increasing. That's a turning point. It's relative to that area, it's a relative minimum. It hits a bottom in an area close to that. And there's another one, there's another one. If you have a degree of 5, then you have 5 minus 1 possible turning points. Or 4. You could have, if the degree is 5, the maximum possible number of turning points is 4. You don't have to have 4, but you could have up to that many. And those turning points are where you get your relative max and relative min points. It's where the graph changes from increasing to decreasing and vice versa. So a little bit about that. So to find all real zeros, we are going to go ahead and factor this. I want to find the zeros. I want to know when y is 0, when it crosses the x-axis. So I'm going to set up solving this for 0. And I'm going to use a sign chart and talk about end behavior in terms of going to graph this. So find all the real zeros, determine maximum possible turning points of the graph, and then sketch the graph. And so as I go through, they each have a common monomial factor of x. So I can pull that out and then just keep that x there. And this x squared minus 12x, it's a perfect square trinomial. It factors into x minus 6 times x minus 6. And again, I need the equals 0 equals 0. And so this right here, don't forget this. This could be written as x minus 0. It produces, that means 0 itself is a solution. Think about it. If I let x be 0, doesn't that whole thing become 0? So x could be 0 or 6 or 6. And we call this a double root. And when you get two of the same quantities, we're going to expect that the graph kind of hits the x-axis and bounces back in the same direction. We'll see that as we sketch that. All right, so maximum number of turning points. So turning points, excuse me, is n minus 1. And the degree of this is 3. So the maximum number of turning points is 2. Maximum number of turning points is 2. Then since we just talked about end behavior, let's look at what we expect for end behavior on this. Right, end behavior. And end behavior, as this is odd, but the leading coefficient's positive, so I expect it to look like this, like an x cubed graph, not flipped. So as x goes to negative infinity, then I expect f of x to also be going to negative infinity. As x goes to positive infinity, then I expect f of x to go to positive infinity as well. So on the left, it's going to go down, and on the right, it is going to go up. On the right, I expect it to go up. So I'm just examining all these. I know zeros are at 0 and at 1, 2, 3, 4, 5, and at 6, because those are x values for which they make y 0. And so as I look at this, I've got this interval of x's. And so what I'm going to do is what we call a sign test. And I want this on your papers. And so each distance between the zeros is an interval. So I'm going to say my first interval is from negative infinity to that x value of 0. My second interval is between those two zeros, and that would be from 0 to 6. And then my last interval starts at 6 and keeps on going to positive infinity. So just split up and name the intervals between the zeros. Now I'm going to go ahead and erase the dots in here because I don't really want those in there. But that's what we're just thinking about. And so what I'm going to do is I'm going to test the sign of the function in each of these intervals. And so I'm going to choose a test number that is inside the interval. It can't be the endpoints, not 0 or negative infinity or 6. So some x value in this interval, well, smaller is probably better for what I'm going to do, so I'm going to pick -1. And then I've got the factored form, and that's the form you want to plug into. And we're just interested in the signs of each of these quantities if x is negative. So if x is -1, this is negative. If I put -1 into the second one, -1 minus 6 is -7. It's negative. I'm not so much concerned about the value as the sign of it. Is it positive or negative? I put -1 in for x here, I get -7, so it's negative. And since these are a product, I'm going to get a negative times a negative times a negative. And if you multiply 3 negatives, you get negative. That means this graph on this interval should be graphing below the x-axis. So on the interval from negative infinity to 0, the graph of the function better be below the x-axis. Then move to this interval from 0 to 6 and pick an x value inside that. Don't pick the endpoints. Don't pick 0 or 6. 1 sounds like a good value because it's nice and small to work with. And again, think about it. Well, if x is 1, that's a positive value. If I put 1 into the second one, I get 1 minus 6, which is a -5, which is negative. And if I put 1 into the third one, 1 minus 6 is also negative. But a positive times a negative is positive. So in that interval, I expect the graph of the function to be above the x-axis because I'm getting positive values. Lastly, then, I'm going to take this interval to the right of 6 and pick a test number. And I like smaller numbers if I can use it, so I'm going to use 7. And think about plugging into the factored form. Well, a positive 7 the first term is positive because 7 is positive. If I put into the next one, 7 minus 6 produces a positive 1. If I put into the third one, 7 minus 6 is a positive 1, so it's positive. And a positive times a positive is a positive. So again, the function is going to go and be above the graph there. And so the idea is I'm going to think about end behavior. It starts down and ends up because it's an x cubed with a positive coefficient. And I've got my zeros. And so I just need this to be looking like a polynomial, a smooth, continuous curve that starts negative, comes up. Now, it's going to bounce at 6. It's going to come and turn and hit the graph and go back up, but it needs to look like a polynomial, so it needs to be smooth. So as I come up, I need to think I've got to turn, come down, and just have it touch at 6 and then go back in a positive direction. And so I'm not even checking other points. How high do I go right here? Well, if I started plugging in points, I could get some actual values and be more accurate, but this is kind of just a general sketch, looking that it looks smooth like a polynomial, that it has the correct end behavior, and that the zeros are in the correct spot. One other thing you could check is the y-intercept. That occurs when x is 0. And if I get f of 0, I get 0 cubed minus 12 times 0 squared plus 36 times 0. This one's unique in that those all come out to 0. And we already had the y-intercept because it happened to also be an x-intercept. So that would be where we are done there for sketching. So I expect this whole sign test analysis. I expect the whole end behavior analysis. I need to see how you break it up and find the x-intercepts so that you can get the intervals, and then you need to graph it. Again, we're not plugging in specific points, not that you couldn't to get a little bit more accurate curve, but it's just the general nature of the shape of it through this exact type of analysis. You can check on Desmos or something, but you need to not go to a graphing utility to get your answer. You need to go through the analysis, and your work must support that you went through all of that.